Academy of Mathematics and System Sciences. And today he'll be talking about the global hydrostatic approximation of hyperbolic Navier-Stokes system with small Gevrey class 2 data. So over to you.
Thank you, Professor Barker. Thanks. First, I would like to thank the organizer for the kind of invitation. It's really my great pleasure and honor to give this talk. So today I'm going to talk about global hydrostatic approximation of a hyperbolic Navier-Stokes system with small Gevrey class 2 data. This is a joint work with Paicu. So let me first recall you this derivation of hyperbolic Prandtl system. The Navier-Stokes equation governing the involution of Newtonian viscous fluids is obtained from the momentum equation partial T of U plus U dot gradient of U equals divergence of tau. So here, this tau is described by the stress tense tau is given by like minus tau of T equals minus P times identity matrix plus this viscosity nu times this matrix gradient of U plus the transverse matrix gradient of U at the time t. So here U stands for the velocity field, P the scalar pressure function, and nu the viscosity coefficient of the fluid. So however, these equations we just recalled gives rise to a physical paradox. The heat transfer has infinite propagation speed. So to avoid this non-physical aspect, Cattaneo in 1949, see also the note in 1961, proposed to modify this heat equation in a hyperbolic version known as Cattaneo's heat transfer law. This leads to the hyperbolic version of Navier-Stokes system. So compared with the classical Navier-Stokes system, we have a term like eta partial t squared of U. It's called hyperbolic Navier-Stokes system. So there are many results concerning the well-posedness of this system. For example, the following paper by Fourier and his collaborators. On the other hand, in order to describe geophysical fluids on the Earth, it's usually assumed that the vertical scale is much smaller than horizontal one because the fluid layer depth is small compared to the radius of the Earth. So in this case, we consider this hyperbolic Navier-Stokes system in a very thin strip as epsilon equals R times 0 to epsilon, and for vanished viscosity, nu equals epsilon squared. And then we implement this hyperbolic Navier-Stokes system with a non-slip bound condition U at Y equals 0 equals U at Y equals epsilon equals 0. And with niche data of this type, U0 xy over epsilon, epsilon V0 xy over epsilon, and this U0 V0 satisfying divergence-free condition. So given data of this type, we assume the solution is also of this type, like UTXY equals U epsilon TXY over epsilon, epsilon V epsilon TXY over epsilon, and this pressure PTXY equals P epsilon TXY over epsilon. Then the domain will be S, which is a strip with fixed length for Y between 0 and 1. So after this natural change of scale, then this hyperbolic Navier-Stokes system becomes the following scale and an anisotropic hyperbolic Navier-Stokes system as follows. So in particular, formally, as epsilon goes to 0, the second equation becomes like partial Y of P equals 0. So formally, as epsilon goes to 0, all these terms involves coefficient like with epsilon will disappear. We formally obtained this hyperbolic version of this Prandtl system with like partial t squared of U plus this term. and with partial yp equals 0. This uv satisfying divergence free condition and with initial data, u at t equals 0 equals u0, ut at time 0 equals u1, and also with homogeneous boundary condition on this upper boundary and lower boundary. So before I present the main result concerning this system, let me recall you some related results for the classical Prandtl system. In 1904, in order to explain this discrepancy of the boundary condition for Navier-Stokes system and ideal fluids on the upspace, in 1904, Prandtl derived this Prandtl system for the fluid in a very thin strip around the boundary, like if the viscosity is like epsilon square in the very small neighborhood of the boundary, like length of epsilon, the fluid should satisfy this Prandtl system. So here, this UV represents this tangential and normal velocities of the boundary layer fluid. W and P are traces of the tangential velocity and pressure of the outflow on the boundary, which is given and are satisfying this Bernoulli's law. In this equation, we have this partial diffusion in the y variable, but we don't have diffusion in the x variable. And we only have this involution equation for this u, but we don't have this involution equation of v. So how we can determine this v? We determine this v by this divergence free condition and also this boundary condition for y when y equals 0 equals 0. So in this way, v almost behaves like minus y times partial x of u. So when you process energy estimate, one derivative will be lost in the horizontal variable, like x variable. So whether or not Prandtl system with general data is well posed in sublet spaces is still open. In 1998, Wiener E and Inquist constructed a class of niche data, like if this class of niche data generates solution, it must blow up in finite time. And Gevrey and Dogme proved sort of well-posedness in sublet spaces for linearized Prandtl system around non-monotone shear flows. And Gevrey and Yengu and Niem also proved sort of nonlinear well-posedness in the sense of non-Lipschitz continuity of the flow. But the classical well-posedness in the sense of Adama is like the solution should be continuously depend on the inch data. So whether or not this problem is well posed in sublet space is still open. So positive results are as follows, like on the monotone assumption on the tangential velocity of the outflow, Analytic in 1963 first introduced Crook transformation to transform the original problem to an approximation equation and proved this log well-posedness of approximation equation and used coordinate transformation to reach the log well-posedness of this classical Prandtl system. With an additional favorable condition on the pressure, Zhu Bingxu and Li Kunzhang can also obtain global existence of weak solution. Recently, Alexander, Wang, Xu, and Yang, and separately by Masmoudi and Wang, instead of using this Crook transformation, by using this engineer's use of the cancellation property of the beta terms containing the tangential derivative, they also proves local existence of a small solution with niche data in sublet space, while energy estimate in weighted sublet spaces. With analytic data, Sammartino and Cavendish first proved in 1998 local well-posedness of this system with data which is analytic in both X and Y variable. In fact, this analyticity in the Y variable assumption was removed by Lombardo, Cattaneo, and San Martino in 2003. The main argument used in the above papers is to apply this abstract Cauchy-Kovalevskaya type theorem. And the David Gevrey and Masmodi can even prove sort of local well-posedness for a class of data with Gevrey regularity. And Vishili and Tongyam can prove this local well-posedness in optimal Gevrey class with non-degenerate critical points. And this result was improved to be optimal in the sense of Dierdek and David Gevrey by Dierdek and David Gevrey in 2019. Concerning the small data for the long time existence, the first result is due to myself and Zhang. We can prove for analytic data of size epsilon, the lifespan could be like epsilon to the -4/3. And this result was soon improved by Ignatova and Vico in 2016 to be almost global existence result. On the other hand, in this book, famous book by Olenek and Samokin, Mathematical Models in Boundary Layer Theory in 1990, on page 15, they listed many open problems, among which the open problem 4 is as follows. It has been shown in chapter 4 that under certain assumptions, a system of non-stationary two-dimensional boundary layer admits one and only one solution in this domain D for either for small enough t for any x greater than 0 or small enough x and for any t greater than 0. So the question is like, what are the conditions ensuring the existence and the uniqueness of solutions of the non-stationary Prandtl system in the domain D with arbitrary x and a capital T? So my first result in this direction for its joint work with Maurice Paicu is concerning the global well-posedness of the Prandtl system with small and analytic data. In this case, just for simplicity, we assume the far-field velocity f only depends on the time variable. We assume that let delta be positive and hf belongs to h1 and satisfying this condition because this u0 v0 satisfying this divergence condition in two space dimension, we can find a potential function such that this u0 equals partial y phi 0. We assume this compatibility condition u0 x0 equals 0, and we also need to assume the integral from 0 to infinity u0 dy equals 0. And we assume the initial data is analytic, which means this E delta D of X act on this initial data belongs to some space here. We belongs to B1/2 0, which means in the X variable, it belongs base of space with half derivative. And in the Y variable, we do not need any derivative. We also need this data decays sufficiently fast when y goes to infinity. To obtain this optimal decay rate with respect to time, we choose this weighted function to be e to the y squared over 8. And the main novelty of this paper is that we introduced a function called a good function, this g0 equals u0 plus y over 2 times phi 0, which satisfies this smallness condition. We can prove this Prandtl system has a unique global solution. Moreover, we can have this propagation of regularity. Like initially, the analytic radius is delta. For t greater than 0, we can prove this analytic radius like delta over 2. For the weighted function here is like e to the y squared over 8. And here, for the solution, the weighted function is e to the y squared over 8 times bracket of t. And we can also prove the decay rates for the solution. Like u itself should decay like t to the minus 3/2. And this good function decays like t to the minus 5 over 4. And if we replace this weighted function e to the y squared over 8 times t by e to the gamma y squared over 8, we can prove the solution u decays with the same rate as this good function g here. Here, this gamma is any positive constant between 0 and 1. So as we mentioned before, Diadec and David Gevrey also proves local well-posedness for the Prandtl system with initial data in the Gevrey class 2. Correspondingly, we also have global well-posedness for this system with initial data in this Gevrey class 2. Here, just for simplicity, we assumed the far field velocity u equals 0. Then by this Bernoulli law, we have this pressure equals some constant. So in this way, the original Prandtl system can be reduced to this form. So here we denote this bracket cosine equals 1 plus cosine squared to the power 1 over 2. And this Fourier multiplier e phi t dx equals e to the delta d square root of this d. Okay, so here, like the initial Gevrey radius is like delta. For t greater than 0, this Gevrey radius should decrease according to the rate like minus lambda times theta of t. And the Fy here means this Fourier multiplier f act on this f, So here we also need to use this anisotropic sublet space, which means you have s derivative in x variable and you have k derivative with respect to y variable. We also need this weighted function here, cosine ty equals y squared over 8 times t. Joint work with Chao Wang and Yuxi Wang, we can prove giving u0 equals partial y phi 0, which satisfies this compatibility condition, and also this integral of u0 with respect to y equals 0, we can prove for small enough but fixed eta between 0 to 1 over 6. We denote this energy functional et as follows, like u phi itself with the weighted function like t to the 1 minus eta over 4. So this part, we have 11 over 2 derivative with x variable. For the y variable, we do not have any derivative. Just as this scenario for the classical Navier-Stokes system, if u itself decays like t to the minus s, the derivative should have like additional 1/2 decay. Here, u itself decays like according to 1 minus eta over 4. So if we take partial y, this decay rate should be 3 minus eta over 4. Okay, and for this good function, the decay rate is like 5 minus eta over 4. And if we take y derivative with respect to y variable, the decay rate should have this additional 1/2. Because here, we shall use this commutative estimate between power product with the Fourier multiplier I just introduced. For high derivative of this good function, we do not need to estimate the Gevrey in the Gevrey class, just a classical anisotropic sublet norm. Okay, and also partial y squared, partial y to the cube of g. With this energy functional, we also have this dissipation of energy, like corresponding to this u here, we have this partial yu phi here. Corresponding to this partial yu phi here, we have partial y squared of u here, and so on. So we assume, moreover, if this u phi 0 in the anisotropic sublet space, h25 over 40 plus the initial energy to be sufficiently small, we can prove the global unique solution of this Prandtl system with niche data satisfy this condition, and moreover, the solution satisfying this energy estimate. So here we have some remarks. As in Diadec and WWZ1, there is loss of Gevrey radius of the solution. And moreover, here we just need additional derivative for the niche data, like U0 phi belongs to H 25/40 to guarantee the solution belongs to H phi 11/20. So this loss of regularity is due to the instability of this problem. And moreover, compared with the previous result with Paicu with analytic data, here our smallness condition cannot be presumed on the niche data, of the good quantity. Moreover, the decay of the Gevrey solution has a loss of eta over 4. We do not know if we can get rid of this loss or not. The main idea to prove this result is to combine the method in Diadec and WWZ1, which is based on both a tricky change of unknown and appropriate choice of test function, and the time-weighted energy estimate method introduced by Paicu and myself. Okay, and furthermore, as in our previous paper, we shall use this faster decay estimate of this good quantity G to control this Gevrey radius of the solution, which will be one of the crucial steps to construct the global Gevrey solution. So in order to solve this problem, we are going to paralinearize this Prandtl system first. In this situation, because this Fourier multiplier is not like analytic case, we can have a commutative estimate between this E phi t of x with this power product. So here we first use power product decomposition to decompose u partial x of u to tu h partial of xu and the remaining terms. And here we use this commutator between this E phi with this power product t of h partial x of u. It's like here, okay? So we first have to estimate the commutator estimate between this Fourier multiplier E phi with this power product. So here you see we gain like half derivative. So in order to map continuously from HS to HS, we need an additional term like here. With this additional term, we can prove this term should map continuously from HS to HS. So now by this power product and also this commutator, we linearize the original Prandtl system as follows. Okay, so here this F is like remaining terms. To construct global small solution with Gevrey-2 regularity in the X variable, we need first to modify the definition of this auxiliary function and H phi, which was first introduced by Diadec and WWZ1. So in order to do so, let's recall this cosine phi ty equals y squared over 8 times t. And this ht be a positive non-decreasing function, we define this linearized operator as follows. And also, it's a joint operator with this weight in this way. So we now introduce this function h in this way. And because this u we satisfy this, and we also need to introduce this phi function in this way. Because this u we satisfy divergence condition, we can also from this equation we shall derive an explicit formula for this U phi and V phi. So we have some remarks in order for this definition and H and phi. The reason why we need this function H of t in the joint operator L star is for the purpose of deriving this decay estimate for the solution H, phi, and U. And here, we also use integral from y to be infinity instead of integral from 0 to y is to make the solution H and phi decay sufficiently fast as y approaching to plus infinity. So here we have this additional theta dot t before this term and also this term is for the purpose of controlling the Gevrey radius of the solution and H and phi simultaneously with their norms. This idea goes back to a paper by Zhang to introduce where Schumann introduced the two to make analytic type estimate and controlling the size of an analytic radius simultaneously for the classical Fujita solutions of the Navier-Stokes system. So here by partial y with the equation I just introduced, we got the involution equation, we got the equation for this U phi by using this divergence free condition and integral the resulting equation from y to infinity. We also have an explicit formula for this V phi. Now, with this formula for U phi and V phi, when we substituted these two formulas to the original Prandtl system, we need to take second derivative of theta of t. Let's recall like that in my joint work with Paicu for the classical Prandtl system, here's the involution equation for the theta dot t is like this. But it's impossible for us to compute one more derivative with respect to time. So fortunately, we observe like what we really used in this joint work with Paicu is the large time decay estimate of this term instead of itself. So by calculation, in our case, eventually we choose this evolution equation for theta dot t as follows. Like say dot t equals square root of epsilon to t to the minus beta power. Okay, so the choice of this evolution equation is by computation. Now let's go back to this hyperbolic Prandtl system. So we already observed it's very complicated to prove the global well-posedness for the classical Prandtl system with niche data in the Gevrey class 2. So here for the classical Prandtl, for the hyperbolic Prandtl system, we will see the proof is much easier. In this situation, the first result is like as follows. For initial data, which is satisfying this condition, which means U0, U1, partial y U0 in the Gevrey class 2. So this BS means anisotropic base of space with S derivative in the X variable, but we do not have any derivative in the Y variable. So here, we have this parameter square root A times kappa. We find that this U0 have this additional 1/2 derivative. And if we replace this parameter by A times K, we gain 1/2 derivative. So we assume this H0 1/2 of the initial data is small enough. And also this compatibility condition integral from 0 to 1 U0 dy equals 0 and 0 to 1 uy dy equals 0. Then we can prove this hyperbolic Prandtl system has unique global solution U for any time t greater than 0. And moreover, we can prove this energy of the solution is controlled by the initial energy. So this energy functional is like ek times t u phi partial y u phi partial t u phi L infinity is a sort of propagation regularity. And because of here, with this parameter, we also have this propagation regularity. And this term concerning this dissipation of energy. So here U phi equals this Fourier multiplier E phi Td of x act on this U. Or you can define this phi t cosine in a symbol A minus lambda theta t times modulus square root of cosine. Then we find this U phi ty equals this E phi multiplied by the partial Fourier transform of U with respect to x variable. Then take inverse Fourier transform from cosine to x. K here is a uniform constant, and this kappa being determined by Bangalore inequality on the strip. In fact, with the estimate we just obtained for any s greater than -1/2, and with niche theta satisfying this condition, H0s, U0, U1 to be finite, we can prove the propagation of regularity. Okay. And in order to propagate the regularity of partial square of t of u, we need additional regularity, need additional assumption for the initial data. The reason why we need all this initial condition for this partial t square is due to the estimate of the pressure function. So compared with classical Prandtl system here, this pressure P is not known. I should point out this difficulty later on if I have time. The second result is like with initial data satisfying this uniform smallness condition, we can prove for this scaled hyperbolic Navier-Stokes system has a unique solution, and moreover, the energy of the solution is controlled by the initial energy. The last result is as if this U0 epsilon V epsilon satisfying the condition we just presented, and U0 U1 satisfying this H3 U0 U1 to be finite, and satisfy this compatibility condition, we can prove the difference between the scaled hyperbolic the solution to hyperbolic Navier-Stokes system and the solution of hyperbolic Prandtl system, the difference U epsilon minus U, we denote by W1 epsilon, and V epsilon minus V by W2 epsilon. We can prove this energy of W1 epsilon, W2 epsilon is controlled by the initial energy plus M times epsilon. So this means for epsilon sufficiently small, as long as this initial data satisfies the above assumption, the solution to the hyperbolic Navier-Stokes system should be very close to this hyperbolic Navier-Stokes system. So in fact, before our result, similar result for the classical scaled Navier-Stokes system to hydrostatic equations has been proven in the analytic functional framework by Paicu, Gevrey, Zhang, and myself. And also, similar result for the hyperbolic Navier-Stokes system was proved to the hyperbolic hydrostatic equations, has been proved for analytic initial data, analytic functional framework by Arachi in 2021, that's 2021 or 2022. So now let me outline the proof. To prove, we needed to use this partition leader with the Paicu analysis, like in particular this partition of unity, dyadic operator, like delta kh, which means this frequency cutoff in the x variable such that the frequency is supported on an annulus with radius 2 to the power k. And also we have this partial sum operator sk of HA, which means the frequency cutoff, after the frequency cutoff, the frequency should concentrate on a ball with the radius 2 to the power of k. Okay, so with this dyadic operator, we can define this anisotropic base of space which means you have S derivative in the X variable, but you do not have any derivative in the Y variable. Okay. We also need to use the Sherman-Lechner type space, which means we integral with respect to time first, then we make this summation. We also need this time-weighted Sherman-Lechner type space. The reason why we need this space, because in general, it's impossible to use Gromov type estimate in the framework of Sherman-Lechner type space. So in order to overcome this difficulty, Maurice Paicu and myself introduced this time-weighted space in 2011, in paper in 2011. And here is still crucial for us to use this time-weighted Sherman-Lechner type space. So now let's go back to our problem. S here denotes the strip x, y, and R2 with y between 0 and 1. And now we consider this hyperbolic Prandtl system as follows, with homogeneous boundary condition on the lower boundary and also the upper boundary. So here this U phi means this Fourier multiplier E phi D act on this U here. And because here, this U we satisfy this homogeneous boundary condition, you expect a solution to the decay like e to the minus kappa of t. So here, after calculation, we choose this involution equation for the theta, like theta dot t equals square root of delta to the e to the minus kappa of 2 times t. Okay. So our result is, our first result is as follows. Assume this H0 1/2 U0 U1 norm to be sufficiently small. Then we can prove for this hyperbolic Prandtl system has a unique global solution. And moreover, the energy of the solution is controlled by the initial energy. Okay. Let me outline the proof. First, we add this Fourier multiplier E phi on this involution equation of this hyperbolic Prandtl system. Okay. Here, this dxs denotes Fourier multiplier in horizontal variable with symbol like cosine to the power of s. Okay. Then we add this dialectic operator delta kh on this equation and take L2 inner product of the resulting equation with delta kh partial t u phi, we obtain this equation. Okay. So here for this term, delta kh partial xp phi with delta kh partial t of u phi by using integration pi parts and the homogeneous boundary condition for u and a partial t of u, we can move this partial x from here to be here. Then use divergence condition with partial x of u equals partial y of v. Then use homogeneous boundary condition for this v. We find we can remove this derivative y to be here. And then use partial yp equals 0. We find this term to be 0. Okay. So partial tu phi equals partial tu phi plus lambda dot d of x 1/2 u phi. So if we just observe from this equation, this tells you like gain like 1/4 derivative of partial t of u. But this not enough to overcome the difficulty that like one derivative is lost in a process of this energy estimate. Just as a classical Navier-Stokes system, here this v behaves like a minus y times partial x of u. So this gain like 1/2 derivative is not enough for the energy estimate of this term. So the observation is as follows. We can rewrite this partial tu phi as partial tu phi plus lambda theta dot d of x square root of d of x times u phi. Then we can rewrite this term as follows. But if I substitute this formula to be here and take square we have this term equals lambda theta dot d of x 1/4 times delta kh partial tu phi, and you have lambda to the cube theta dot to the power 3 with 3/2 derivative act on the delta kh uv. And for this term, we can write it in this way. Okay. For the term like minus delta kh partial y squared u phi L2 inner product with delta kh partial tu phi, we can write as this time derivative on this term plus this term for partial y of u, you like again like 1/2 derivative. So eventually this energy for delta kh partial tu phi is like as follows. We will see if this weighted function is like theta dot, you for partial tu phi and partial y phi, you gain 1/2 derivative. And here, if the weighted function is replaced by theta dot to the cube, then we gain like 3/2 derivative. And this gain is enough for us to overcome this loss of 1 derivative. So here, for this energy estimate, we do not have this dissipation like partial y of u. In order to get the other estimate, we take for the original equation, we act this delta kh and I take L2 inner product of the result equation with delta kh u phi, then we reach this equality. Like for this term, we write in this way. For this term, we write in this way. And eventually, we can have a term, have a energy quality as follows. So the advantage of this energy equality is like here, we have delta kh partial uy, u phi here. The disadvantage is like here, we have minus delta kh partial tu phi here. But in the previous energy equality, we have this term with plus sign. So in order to get rid of this minus term, we weight it by summing up this energy inequality with this weight, with the second inequality, we can have this energy, this evolution, this differential equality for this F0 here. Because of the special choice of theta t, it's a concave function, convex function. We have this theta dot of t should be negative, so minus theta double dot of t should be positive. Okay, with 1 dot here, we gain like 1/4 derivative. Square here, we gain 1/2 derivative. Cube here, we gain like 3/4 derivative here. Okay, so this F0, by its definition, and also this coefficient, we can prove this the F0 of t is almost like delta kh partial tu phi, delta k partial yu phi, delta kh u phi, and these terms. Okay, and that's the initial energy B of 0 k of u at time t is defined as follows. Okay, so now in order to close the energy estimate, we need to estimate the right-hand side. So let me present to you the main idea of the proof. We should use by a continuous argument to prove lifespan to be plus infinity. So because as we mentioned, the solution, because the solution is on this strip with homogeneous boundary condition, you expect the solution should decay like e to the minus kappa of t. Okay, let us assume this T0 star should be for t less than this, and with this condition, we can prove for this integral from 0 to t e kappa e k t prime, this weighted function delta k h u partial x of a phi, take L2 in product with e k t prime delta k h b phi L2 norm, how should be estimated on the right-hand side. So you'll see here, we have this additional derivative partial x of u here. How can we compensate this one derivative? We shall use like three-quarter derivative on this Fy here. And we shall use like 1/4 derivative on this B here. The 3/2, 3/4 plus 1/4 derivative compensate this one derivative here. The proof of this lemma is to use like anisotropic bonus decomposition, and by this estimate of the weighted energy space to gain to reach this. So due to time restriction, I'm not going to present a detail on this lemma. And similarly, we can also prove a lemma like this for EKT delta KH V of A take L2 inner product with this term. As we mentioned before, this V is like minus partial x of u. So here again, you have an additional derivative here. In order to get this derivative, we also have this 3/2 derivative on this u and 1/2 derivative on this b. Okay. So with this, we can close the energy estimate. So you see here, compared this proof with the proof for the global well-posedness of classical Prandtl system with optimal Gevrey class data. Here, the proof is much easier. The main reason is because of this second derivative with respect to time t make us to use three time weighted space like L2 theta dot t b 3/2, L2 theta to the cube b 5/4. And in fact, we also have another space E of kt u phi in L2t theta square to b1. Okay. So with this, by taking square root of this inequality on both sides and a sum with respect to k, we reach this energy inequality. In this situation, as long as we take this lambda large enough, this term b3/2 will be absorbed by this term. And for this term, here we have a square root of lambda here, but we have here lambda to 3/2. As long as lambda large enough, this term will be absorbed by the left-hand side. So eventually, we have this partial yu phi should be controlled by the left-hand side. As long as the C0 for the each data is sufficiently small, we can prove this constant is less than or equals to delta over 2 for t less than t0 star. This contradicts with the definition of t0 star, and this in turn shows this t0 star equals plus infinity. Okay, so this proves the global existence of solution. So then finally, let me mention you why the estimate of the pressure function is difficult in this situation. Due to the boundary condition for this V on the lower boundary and the upper boundary, we get by integrating of this partial xu plus partial yu equals 0 on this interval from 0 to 1 in the y variable, we have this condition. As we denote this integral like by f of t, because partial x of this term equals 0, this shows this term is independent of x. So we denote this term by ft, then we can determine the pressure by integral the original equation from 0 to 1 with respect to y variable. We reach an equation like this. Okay. So if we determine the pressure in this way by integrating this equation for y from 0 to 1. We find this F should satisfy the second order ordinary differential equation. Because we assume initially this integral from 0 to 1 u0 dy equals 0, and this integral of this u1 from 0 to 1 dy equals 0, which means initial data of this F at time 0 and first derivative equals 0. So this shows that f of t equals 0. This in turn shows indeed this pressure should be determined by this equation. Okay. So in order to estimate a partial t square of this u, we need to estimate this partial y of u, which corresponds to the vorticity in two-dimensional flow. By using this condition, we find that this omega should satisfy equation like this. So in order to estimate the energy of this partial t omega, it turns out we needed to estimate this partial x of p. Now we already have this formula for this partial x of p. In order to close this estimate, we need additional derivative for initial data. That's the reason why in our first result concerning the estimate of partial t square, we need much more derivative of the initial data. I think my time is almost finished. I'm going to stop here. Thanks a lot for your attention. Thank you.
Thank you very much. Thank you very much for your nice talk. Are there any questions for anyone here physically or on Zoom?
Hey, Ping, nice talk.
Thank you.
So I'm trying to understand a little bit this equation from a more intuitive point of view. So am I correct that of course there are technical different challenges due to the extra term, but because in Prandtl really the time is the, the horizontal variable, in some sense the system is not too far from a standard Prandtl system. And if
Yes.
Okay, and if then do you expect that you might have finite time singularities of the Van Dommelen type even for this system?
For the singularity of this system?
Yeah, like not for small data, of course, for large data, like the Van
Like the
Dommelen
result by Wien and Yi and Inquist.
for example, or the
Yes.
right, based on that, yeah, and the more recent work of Kukavica and Bicol and
Yes.
Yeah.
I think so. For the initial data, I think so. For the large data, the solution should blow up just as the classical Prandtl system. That's my expectation also.
So do you expect that Gevrey 2 is sharp then, or?
In fact, after this result with Paicu, at the beginning we tried very hard. We expect the optimal index should be like 1/4 instead of 1/2, because here this Gevrey 2 we can obtain by classical energy estimate. We trying to use this idea by Dietrich and David Gevrey, but it turns out this method does not work. The reason is because here we use two energy estimates. Here we perform the energy estimate as the one by Dietrich and David Gevrey. We have additional difficulty to deal with energy estimate like u partial x of u with partial t of u. That's the main difficulty. So u partial x of u is not a difficulty in the original Prandtl system. But here, for hyperbolic Prandtl system, we have another energy estimate like u partial x of u with partial t of u. And this term turns out a big difficulty that we cannot improve this regularity index. This
Okay,
I'm not so sure.
okay, thank you very much.
Thank you.
So we have a couple of questions from Zoom, from our online speakers.
Let's unmute Idris. Idris is unmuted, so he can.
Oh, okay.
Over to you, Idris.
Yes. Hi, Bing. Thank you for
Hi.
thank you for the nice talk. Very technical,
Professor
very
DG.
solid. Yeah, I have actually a couple of comments. Certainly, the work is outstanding and very technical.
Thank you.
I just basically wanted to draw some analogies and about the technical aspect. This idea with this particular multiplier e to the power, etc., was first introduced by Fourier and Timam in the context of Navier-Stokes, and it made life much easier in that direction. And then many people followed, in particular Livermore and Oliver for the Euler equation and so on and so forth. So just to put things in context, that there was some work, especially really controlling this radius of analyticity, your exponent there. It has been a lot of work in this direction. So this is the one thing I wanted to mention on a historical note. So life started already a long time ago. This is work from the late 1980s. The other thing I want to mention to draw the attention, even though the Prandtl equation is has its own entity and its own difficulties and challenges, etc., there is a lot of similarity with the what we call the primitive equations in atmospheric and oceanic dynamics. And some of those ideas, I mean, even though it's not the same because the challenge in Prandtl is different, there's a lot of similarities in the derivation and similarities in the results and the tools. And so I would like to draw the analogy because there is a big, huge body of work about the primitive equations.
Yes.
Which is really related to this lecture. One third thing is there are two communities which is try to regularize Navier-Stokes equation, or three communities. One is you take Navier-Stokes and add hyperviscosity. The problem usually with hyperviscosity, which is people use in simulation in big ocean codes and atmospheric codes, is that you need an artificial boundary condition for the hyperviscosity, because it's higher order Laplacian requires boundary condition, and this will require artificial boundary conditions. So this is really an issue. The other community, which is basically what you mentioned here, is you take Navier-Stokes and you regularize it by adding two time derivatives, becoming hyperbolic. This, on the other hand, would require, in some sense, to giving you initial data for the time derivative, which is you don't have unless you would like to do some compatibility that the Navier-Stokes should apply or should be valid at time zero to conclude what should be the time derivative at time zero. Now, the third community, which is I basically belong to, one option to regularize it for numerical purposes and otherwise is what we call Navier-Stokes void regularization. Namely, you add minus Laplacian of the time derivative. And this is, I call implicit regularization, which is similar in some sense to your hyperbolic regularization because it does not dissipate energy. It basically what it does, because this is a workshop on turbulence, it inhibits the cascade of energy at scale, where basically if you have the term minus alpha square Laplacian t, so alpha is a length scale, it inhibits the cascade of energy at length scale below alpha. So it slows the cascade of energy, and hence, in some sense, it is preventing the formation of singularity because it slows down the cascade of energy to the smaller and smaller scales. Now, the reason I like this, what I call the Navier-Stokes void, or we call it Navier-Stokes regularization, which is in fact has been introduced by a student of Lazhanskaya, Skolkov, long time ago in the 70s, to regularize Navier-Stokes, is basically that the boundary condition required is on the time derivative. Now it's boundary condition, and if u is given at the boundary, then one can derive automatically the time derivative. And there is also work, as I mentioned, which is analog to what you did for regularization of equations like the primitive equation with the void model. So it's not more a question more than comment to put things in context that there is an analog body of work which is parallel, and there is analogy between the primitive equations and the Prandtl equation, despite, as I mentioned, primitive equation has its own subtle issues and technical issues, which is you outlined beautifully in your lecture. Thank you very much.
Thank you, Professor Titi. In fact, I spent some time to read the papers you sent me before, but I still have not finished yet. I'm holding, I think I may contact you later after I have more questions concerning this atmosphere.
No, that's fine. I just wanted to draw the analogy because there are two bodies of work. And as I said, the equations are slightly different, but there is a lot of analogy, especially that both enjoy the hydrostatic balance. And therefore, there is some similar technical issues, but they are different systems, I can assure you.
Okay, thank you.
Okay, so we'll go to a Zoom question from Stephen Cowley.
Can I ask a question? I may have missed it. I thought that you were solving in a channel, i.e. y is between 0 and 1, rather than a semi-infinite space. Is that correct?
Can you, pardon? I did not hear clearly.
So I thought that the domain you were solving on was between y equals 0 and y equals 1,
right,
rather than y equals 0 and y equals infinity. Is that correct?
Y equals infinity, there's a problem is much more difficult in this situation.
Okay. No, but I
don't know how to prove for the time being.
Right, but if you're doing it in a channel between 0 and 1, then I don't think you can get a Van Dommelin and Shen singularity, because the nature of the singularity is that the particle gets squashed to 0 thickness in the x direction, which then pushes the vorticity above that particle out to infinity. And because of the fact that you've actually got a lid on, sorry, I'm using plumbing terms, you've got a lid on your box, you can't get a Van Dommelin singularity. That doesn't mean you can't get another type of singularity, but it will not be a Van Dommelin singularity because the physics forbids it.
Okay, thank you. Thank you for your comment.
Any further questions? If not, let's thank Pin again for a great talk.
Thank you very much. Thank you.
Thank you again. Thank you.
Thank you, Professor Titi.